Okay, so in this section we're going to discuss 3.1. It's all about functions, and we're going to talk about the definition of a function, properties of functions, we'll talk about interval notation again, and we'll talk about the difference quotient. Alright, so the definition of a function. So a function consists of a set of inputs, or x values, that we call the domain. It also has a set of outputs that we call the range, which are the y values, and then some kind of rule that applies to the input that results in the output, or the domain and range, that determines that exactly one output corresponds for each input. So if we plug in x is 2, we can only get out one y, or one output, when x is 2. Here would be an example of a function. Sales tax in North Carolina, that's 4.75%. So let's say you go to your favorite clothing store. Each item costs an X number of dollars. Then when we find the sales tax T, we can do that by using the function. T of X is equal to 0.0475 times the number of dollars for the price of the shirt, or X. The difference in a function versus some kind of equation is that the function allows us to choose our x value, and we can try any x value to spit out an output or a y value. So functions are represented by f parentheses x, which is read as f of x. So for this function, so f is the name of the function. X is the input. F of x is the output. F of x is is interchangeable with y, so y and f of x can be viewed the same. And then the rule that's being applied for this case would be we're taking the square root of the input squared and subtracting 1 from it. So if we're multiplying it by 2, then that would be the rule. Adding 12 to it, the input, that would be the rule. Okay, so whatever rule it is, it just has to correspond that exactly, or each input corresponds to exactly one output. Here's just an example of a function, and that should be 5,000. So a personal loan of 5,000 has an interest rate of 15.25% for 5 years, and we can represent that function of the loan balance as a table or a graph. So we can represent functions as both tables and graphs. So just noticing, we have in the left column our years, which is our x values, and then whatever function for the loan balance in the right column, and that corresponds also to the graph shown. For each year, we have a certain output that's represented by a number on this given curve. So each function has a specified domain, and they're represented by using interval notation. So it has a set of x values that the function can take. So just for the first one, I'm looking for any potential x values that could be a problem. Okay, one quick way is to graph this. So if you want to go ahead and pause it, pause the video and plug this into Desmos and get out a graph. Okay, so assuming that you did that, you would see that the domain for this given function is negative infinity all the way up to infinity. So there are no x values that would be potential issues. Anytime that you have something that's like a linear or quadratic, any of those types of functions, you're not going to have any problems. However, for g of x and h of x, we could have some potential problems. So for g of x, which is x divided by x squared plus x minus 2, we know that we cannot divide by 0. So therefore, x squared plus x minus 2 can't be 0. You can use equals or not equals here. That's totally up to you as long as you know what you're referring to. So I want to identify when the denominator would be equal to 0, and I do that with factoring. So multiples of negative 2 are either 1 and negative 2 or negative 1 and 2. And which of those multiply together to give me, add together to give me positive 1? That would mean my factors are x plus 2 and x minus 1. Solving each of these, I get x is negative 2 and x is 1. So I cannot have x be negative 2 or x be 1, or I'm going to have some kind of hole or an asymptote or something in my graph that the function just would not exist at these values. So how I represent the domain, I say from negative infinity all the way up to negative 2, or from negative 2 to 1, or from 1 to positive infinity. So as long as the values are inside these specified intervals, then I should have no problem, okay? By using the parenthesis, I'm saying that I'm going to get really close to negative 2, but I'll never actually be negative 2. I'm going to get really close to 1, but I'll never actually be at 1, okay? So that's how we use parentheses to represent open intervals. All right, and our last one, if you graph this again, so h of x is square root of 16 minus x, okay? So what will happen, you'll get a graph, and then at 16, and it should look something like this. Okay, so what this is saying is an interval is that anything less than 16, I'm good. So I can go all the way down to negative infinity. At 16, I'm also good because 16 minus 16 is 0. Square root of 0 is just 0. So I can include 16 in my interval. And then also, as you can see from the graph, nothing exists to the right of 16. So this would be my domain for that given function. So anytime we're dividing by 0, or anytime we have a fraction, we can't divide by 0. If we have a some kind of like square root or fourth root, any even power root, then we can't be negative. So 16 minus x. So I couldn't put in 17 because 16 minus 17 would be 1 or negative 1. Square root of negative 1 is a complex number that we won't discuss in this class. All right, so to talk about evaluating functions, so let S of t represent the number of students in class, and S is a function of time t. So what is S of 20 equal 35? What does that really represent? So what I'm saying here is that at time 20, there were 35 students in class. You know, the same way at month 4, there were, you know, the stock was worth $100, okay? So S of 4 would be equal to 100. So that's just putting into context, you know, what this function notation really means. All right, so let's talk about evaluating functions. So for f of 3, then I am just going to replace my input So my input was x in the original function. So wherever I see an x, I'm just going to plug in 3. So I have 2 times 3 squared plus 1. So 2 times 3 squared, that's 9 plus 1, 18 plus 1, so that comes out to 19. So that's my goal for all these examples. So I'm just going to evaluate the functions at these given points. Okay, so for this example, we did get a number value back out for our output. Okay, for our second example, we have f of 7x is equal to 2 times 7x squared plus 1. So 2 times, so 7 squared, that's 49, x squared plus 1. 2 times 49 is 98x squared plus 1. Okay, so for this one, we have a variable as an output for a function, but that's okay because we were putting a variable in the input, so we would anticipate that to happen. And so for the last example, I have f of x plus h. So I'm going to replace all my x's in the original with x plus h. So I have 2 times x plus h squared plus 1. That's the same thing as saying 2 times x plus h times x plus h plus 1. So I'm going to distribute this out, FOIL it. So I have x squared, x times x is x squared, plus xh plus xh plus h squared plus 1. And so then I distribute the 2 all the way through, so I get 2x squared plus 4xh plus 2h squared plus 1. Okay, and so that's just another example of evaluating a function. Again, we just take whatever our new input is, so in this case x plus h, and plug it in for wherever we see an x, and then simplify it as far as possible. And so that leads into our concept of a difference quotient. So the difference quotient is represented by this function. So we have f of x plus h minus the original function f of x, all divided by h. So let's find the difference quotient of x squared plus 1. So I already have f of x as x squared plus 1, so I don't have to do anything with that. But I do need to find f of x plus h. And so I do that by replacing, so x plus h squared plus 1. I'm going to just go ahead and skip and show the final result of this. If you have issues on the FOILing, just refer to the previous example, but it's x squared plus 2xh plus h squared plus 1. Okay, so now I want to take this new x plus h and plug it into the difference quotient. So I have x squared plus 2xh plus h squared plus 1 minus the original function of x squared plus 1, and that whole thing is divided by h. Okay, so if I look here at some like terms, I can go ahead and simplify. So I have an x squared minus x squared, so I can get rid of that. I have 1 minus 1, so I can get rid of that. So that leaves me with 2xh plus h squared divided by h. These all have a common h, so I can get rid of those or divide those out. So my final result is 2x. Well, let me write it up here. So my final result is 2x plus h, and that would be my difference quotient for this given function. The difference quotient is used as a basis of calculus, so we'll discuss this more later, but just so you see it and know what to expect. And with that being said, that does conclude the section of 3.1. So if you have any questions, please feel free to email me. Chapter 3 will be our last topic before we take the exam. Thank you and have a great rest of your day.